39 international publications and conferences and holds one Indian patent. His research area includes reliability aspects of power electronic converters and optimization techniques and assistive technology. With this introduction, I request Dr. Sankar Padapati Garu to deliver his lecture.
Meanwhile, I have requested our resource person to interact with the participants so that any areas of interest regarding research or how to do your current work will be answered by him for the first 20 minutes. Later on, sir will start the session. So I request our participants to clear your queries, if any. Please use this opportunity.
Maybe during session. Okay. Okay. In case of electric vehicles, there are many opportunities. As sir already pointed out, multiple points. One is like charging infrastructure. Charging infrastructure is one area we can look. You know that. So charging in the sense, one is the chargers should support vehicle to grid as well as grid to vehicle concept. So like one word people are talking about is vehicle to grid and grid to vehicle. Okay, so the infrastructure perspective, charging infrastructure perspective, where we can able to send the power from grid to electric vehicle, that is simply charging, or from vehicle to grid. So that is one area where people can work. So there are actually a lot of challenges. Actually, with respect to converter level itself, there are a lot of challenges. For example, many people know about one important application, one important parameter is the weight. When it comes to electric vehicle, weight is one important parameter. So other important parameter is like efficiency. Efficiency is another important parameter. So actually they are actually related. Actually, efficiency and weight are both related, because if we have a power converter, like if we are talking about SAW switching, I mean where the power losses are less, then we know amount of heat sink required is very small. So weight and weight as well as efficiency is correlative. Similarly, if you talk about electric vehicle, one important application or one important area is a traction. People are working in terms of algorithms like how to minimize the torque ripples, in electrical machine. For example, you have PMSM motor, you have BLDC motor, you have induction motor. Like in industry, people are going with PMSM motor only. Okay, for PMSM motor, what are the different algorithms like in order to reduce the ripples in the torque? So that is one area people are like more people are working in reducing the ripples in the torque. Okay, another area people are working in the traction is a fault tolerant topologies. For example, they talk in terms of machine. People took like five-phase machine. Then if some fault is there on one of the winding, then how do you how do you use the other windings to see that electric vehicle is basically moving? Though there is a fault at the winding, but how the other windings are used to move the electrical vehicle on the road. So that is one area people are working. The other is with respect to converters itself. Like I'll show you one slide I have that how the power converters, like using some redundant legs. Like if there is a fault in the inverter, basically you know that electric vehicles are more sensitive, and the semiconductor devices are more fault prone. So they are subjected to no fail actually because of if the semiconductor devices experiences some high voltage stress or high current stress, then they tend to fail. So if the semiconductor fails, then how can we make the other semiconductor devices to run? That is called fault tolerant inverters. Similarly, multi-level inverters also people are working in electrical vehicle application. Okay, when it comes to DC-DC converters, like I'll show you, like people are also using DC-DC converters in electric vehicles, because you know that nowadays if you take any high-end car, multiple motors are coming, multiple motors. Like it could be a wiper motor, it could be motors required for opening the door, or it could be opening the slide window, or it could be opening simple locks. So people are using a lot of motors. For every motor, some different DC voltage rails are required. So in-house, in electric vehicles itself, multiple voltage levels are required. So people are working in DC-DC converters also. And similarly, one important requirement when it comes to charging infrastructure is, of course, fast charging we are always talking about, and then resonant converters plays an important role in that, especially while it comes to wireless transmission. There is a like a sending coil and then receiving end coil. In between, air is a medium actually. So how the energy can be transferred to the battery? Energy can be transferred to the battery from charging infrastructure is one major challenge. And when it comes, there are some actually major other major challenges are like if you take about simple charging infrastructure, battery if you take, so battery it should have less ripples. Like voltage ripples and current ripples plays an important role in the life of the battery. So a DC-DC converter if you want to develop, or a converter if you want to develop for a charging infrastructure, you see that the ripples are less at the battery level. At the same time, it should be a bidirectional supply. So both it should transfer the power from grid to, as I told, like grid to vehicle and vehicle to grid. It requires a bidirectional power flow. For example, sometimes even we talk about regenerative braking also. From motor also we fed back or we collect the power from the motor, and then we fed back to the battery. Like that, electric vehicles is concerned, like parallel operation is another challenge actually. For example, I have five, I have a charger. I have two chargers, for example. Like people are talking about how do you take the input of two chargers to give or to do fast charging of a given electric vehicle. Like existing infrastructure with small modifications. People are looking with small level research also. Like how do we make a parallelize? So how do you exactly do the power matching? For example, if I require 10 kilowatt, but if I have a one charger is rating is 7 kilowatt and other is some 3 kilowatt, then how do you able to do the power management? So you see to see that the charging is at faster rate. Okay, like that multiple areas are there, and one more area is like people those who are good at like physics and as well as some simulation tools, then you can work in code design of a electrical machine. So for example, like you previously like induction motor we have, then PMS motor recently it has like most of the electrical vehicles we use PMSM only. So people working in how do you design the windings. So to see that the flux is uniform and it is rotating, like it produces rotating, continuous rotating magnetic field in the air gap. That means design on the machine also is one aspect. Another aspect is in the same machine design, the gearless motors. For example, if, there are multiple requirements for a motor. You know that for electric vehicle at the time of starting, we require a low speed and high torque. But when we are running at higher speed, then we require like low torque actually. So there is one, what actually we do is we use a gear system. Generally gear systems are not that much efficient system. So though efficient in the sense, always mechanical gears has some losses. We know that. So it has some losses. If you avoid the gears, then we can improve the performance also. So people are designing some kind of a motor structure, motor like complete design to avoid the sensors at the sensors, mechanical sensors. Some people are also thinking about um, like like as I told, regenerative braking. So even in regenerative braking cases also, how the motor design will help us to do the better regenerative braking also. So unlike power converter stage, like we basically have some different criteria if we want to do a regenerative braking. For example, if it is an induction motor, we need to operate the induction motor at negative sleep. If the same is a like a DC motor or DC generator, DC generator, like two reverse, then we know that generated EMF should be greater than the applied voltage. So here they are looking into the structure of the winding itself, reconfiguring the winding itself to do the regenerative braking, unlike a power converter based regenerative braking. Like that, so many works are coming now. So yeah. So with this, there are scope actually. Even while session also, I'll address something. I think we can start now. Hmm? Hmm, hmm. Is it audible? On only. It's audible. Okay. Sir, okay, okay, fine. Mm, mm, mm. ఇక్కడికి రా ఇది ఇక్కడికి వస్తాను ఇక్కడ ఉంటాను ఐల్ బి హియర్ ఐల్ బి హియర్ కంటిన్యూస్లీ ఐల్ బి హియర్ యూ కెన్ రొటేట్ లైక్ దిస్ ఆల్సో కొంచెం చూడండి ఇప్పుడు చూడండి ఒకసారి ఓకే it is like this. It is little slow, I think. Okay, okay. Okay, fine. Okay, I'll be here, no issue. Yeah. Okay, today's topic is like we see some power converters in electric vehicles, like the operation also. We'll see. Um, Generally, why power conversion, power electronics is important is, you know that here, I'll move like this because you are here. So power electronics we use for power conversion, that we know, like you know that our utility is sometimes at different voltage and our loads are at different voltage. Our generation is at different voltages. So it is always required to map the or the voltage profiles. For example, some load demands some voltage profile. If you want to reduce the same load, we need to have different voltage magnitude. So this power conversion will help us to match the loads as well as the source profile. Okay, there is a device actually, we need to map the source profile and the load profile. So for that we need a power conversion device. Similarly, power converter devices are also helpful for power conditioning. You know that in the previous case, like we have seen that there was some small regulators, right? Small regulators to change our fan speed, SCR based regulators, but they actually create some kind of harmonics. Okay, and the same power electronics we can use for power conditioning also. For example, like the load is demanding I plus IH, I plus IH. The load is demanding I plus IH, where IH is nothing but harmonics. I is a fundamental component. Then, if you locally give IH in the reverse direction, if you locally give IH in reverse direction, then what is the current from coming from the grid? It is only I, because IH you are cancelling. I plus IH, and you are giving IH in the opposite direction. Then what is the current from the grid? It is only I. That means this power converters, this power conditioning equipment is used for even cancelling the harmonics also. Technically, they are named as active shunt filter. Similarly, there are many applications of power conditioning. Like, for example, if I want to supply the reactive power also, you can supply the reactive power. Sometimes, the grid demands like more reactive power. Then, especially during the short, different fault conditions, then the power converters basically through STATCOM, in the name of STATCOM and all, we can able to give the reactive power to the grid. Okay, like that there are so many power conditioning devices. So to maintain the like a grid stable. And the next is impedance matching, especially when it comes to solar. We talk about this impedance matching. It is like this. You know that as per the maximum power transfer theorem, everyone knows that, right? So if you want to transfer the power from source to load, then the source impedance must be equal to load impedance. So here, the impedance matching we can do, like, especially when it comes to solar, the solar irradiation and temperature varies actually. If solar irradiation and temperature varies, then the maximum resistance of the solar, I mean the power at peak power at the maximum resistance, it varies. So it is important to capture that power. So for that, you have to operate the DC-DC converter such that you vary the effective resistance so that you can track the maximum power from the solar. Okay, this is what impedance matching. Then intelligent control. For example, you take in this room, if we able to integrate with IoT, because even our title is also IoT based. So IoT, we can implement IoT. So when we have a power semiconductor devices effectively, so actually it is aiding, because, for example, if I want to turn on air conditioner, here air conditioner I want to turn on, then we know that if I have some Raspberry Pi or ESP32 module, if I interconnect with Wi-Fi, and then if I use some solid state relay, I mean made of some semiconductor devices like power electronics, like MOSFET or IGBT, I can basically turn on the air conditioner or the fan or so and so. So that means this power semiconductor devices or power electronics, so is helping us to do intelligent control. Okay, we can actually integrate the IoT also. Of course, where we use this our systems is, as I told you, transportation, so many power electronic components, then home appliances, industry, electric power generation, so whatnot. Many places we are using these power electronic systems. And coming to some performance indices, if you see a DC-DC converter, like in DC-DC converter, like as I told in the previous itself, like the ripples plays an important role. Like one aspect is efficiency. Efficiency is a very generalized requirement. Another aspect is like the ripples actually. So the ripple should be very minimum, both at the input side as well as the output side, especially to improve the battery life. So DC-DC converters, another important parameter is having the reduced voltage stress, having reduced current stress. Similarly, if you talk about a simple inverter, we know that inverter is desired output is AC, but as I told, DC has ripples, but AC content is measured. The quality of the AC content is measured through THD, total harmonic distortion. So it should be as minimum as possible. And and one more thing is, when we design anything, people look into like what is the VA rating of the switch. So you should see that the VA rating of the switch is minimized. When we designing now, so you should see that the VA rating of the switch is minimized. If it is minimized, the cost of the semiconductor devices can be reduced. Then of course this is very fundamental way, like capital cost and the initial operation and maintenance cost. So we should see that it is minimum, right? So if you look into a total electric vehicle, like this is you can see here I have shown some requirements of power electronics. So one is it is working, but I think on board it is not coming. Anyway. You see that battery charger, then you see the traction drive, and you see the DC-DC converter. These are some three major power electronic components. One is a charger, other is a drive unit, main drive unit, other is a DC-DC converter unit. Okay. So you know that why we need this traction drive is, you know that electric motors is either induction motor type or PMSM motor type. Mostly two motors. I am not considering the other motors because they are not much using nowadays. Okay, but their operating principles are same only. Nowadays, people are looking into SR motors also, switched reluctance motors also. Sine switched reluctance motors people are working actually. But anyway, we will stick to PMSM and the induction motor. So here, what we do was, in case of induction motor, the same drive actually we use like a VFD, like in a variable frequency drive. So we used to maintain V by F constant. So we know the advantage of maintaining the V by F constant because we can use the induction motor at higher rating. So that is one advantage. At the same time, we can improve the efficiency also when we operate at a constant V by F. So we have studied previously. So for V by F control, in case of induction motor, for electronic commutation. So electronic commutation in case of PMSM motor, we need a simple inverter kind of setup. Like, you know, most used inverter setup is like a three-leg inverter. The one which I have shown is a three-leg inverter. So there are people who are using like a multi-level inverter also instead of three-level. But industry is using only three-level. Industry people like hardly they are using like, you know, using like, you know, three-level inverter. Of course, people sometimes this is also called as a two-level inverter also. See, if you talk about inverter, if you measure with respect to pole voltage, that's a two-level inverter. If it is with respect to line to line, it is a three-level inverter. Okay. So most cases, pole voltage is generally considered. Pole voltage means, so from here, I'm unable to see this slide, but this point. So from here to here, if this switch is closed, it is plus VDC. If this switch is closed, it is 0. Okay. So that is 2-level. Otherwise, if it is between line to line, it is a 3-level. Okay. But anyway, so the idea here is we provide a variable frequency like operation to induction motor if it is. Otherwise, in order to create the electromagnetic EMF in rotating magnetic field in stator of PMSM, then we use electronic computation. So this inverter setup will help us to do electronic computation in case of PMSM and VFD in case of induction motor. So ultimately, people are working in developing some algorithms in reducing the torque ripples. Okay. Then coming to this part, DC-DC converters, as I told, like multiple requirements are there, like even small heaters, even air conditioners also in in cars, they work in DC, and similarly headlights require different voltage, USB requires different voltage, and then the speakers require different voltage. So multiple DC levels are required, therefore DC-DC converters are important. Okay, and sometimes people are also integrating electric vehicles with solar. Like, you know, they use solar, like, you know, they cover actually the outer surface with the solar panels. So not like, you know, they are called flexible panels. So they don't have actual glass, but they are flexible, and then they can actually generate the power, and then they'll give it to charging the battery also. But of course, the quantum of power generated is very small. But still, if you look into it now, like what will happen was, you see that I have just shown the importance of electric vehicle. Like, you know, if we are using any PV, so you just see here, PV, we know that PV is made of like, P channel and N channel material, and then if the solar in the form of photons deposit on the in between them, the electron and hole separation take place. Then if external circuit is connected, then current will flow from the external circuit. There are some fingers on the solar panel to collect that current. But the important point here is the voltage is not actually constant. For example, always we intend to track the maximum power. For example, this is a solar power, and if if the irradiation is 1000 watts per meter square, irradiation means you know that. So solar irradiation is 1000 watts per meter square, and this is the maximum operating point. For example, if it is 500 watts per meter square, so this is the maximum watts per meter square. I mean, this is the maximum point. So technically speaking, this is called MPPT, maximum power point tracking, MPP point. This is another MPP point. But one important observation is that is the operating point is not same for different operating conditions. I mean, one maximum is here, another maximum is here, another maximum is here. So it is varying actually. The operating point, the maximum or the optimal operating point is actually varying. Correct, na? So it is always important that even if the optimal operating point is varying, then how the DC-DC converters will help us to inject the power into the grid. Okay, that's one of the application. And similarly, if you take unlike electric vehicles, the other competition for the electric vehicle is hydrogen-based electric vehicles. So there also we demand DC-DC converters. So for example, you see here. Hydrogen and water, we use electricity for the generation of electricity, that is called through fuel cells. So fuel cells also people like like they are actually using, and then always there is a war actually between EV and hydrogen cells. Okay, for example, you see here this is a current and this is a voltage. One observation or one takeaway from this slide is from with respect to voltage and current characteristics of the fuel cell is the voltage is not constant with respect to current. So voltage is decreasing with respect to increasing current. So here also the input, for example, I am using fuel cell, there is a load. There is a load. If a current is varying, then what is happening? The voltage input side is varying. Okay, so voltage input side is varying. So when the input voltage is varying, but we need to maintain the constant voltage, then so you need to use a DC-DC converter. There is no other chance. Input voltage is varying, but you need to maintain other side constant voltage. Then obviously we need to have a DC-DC converter in between. Okay. Okay, this I already told, multiple impedance matching and multiple rails at different voltages. Okay, now if you see a simple DC-DC converters, like there are a couple of DC-DC converters in the literature. One is a buck converter, other is a boost converter, right? We know that, it is very straightforward, like we know, but actually how it is working is, we know that like just imagine that I have a constant voltage. In previous days, what we used to do, if you want to change the DC voltage in previous days, I have a constant voltage, I want to change the voltage at the other side. I have a 10 volts, for example, I want to change the voltage. Potential divider is the one way, like we use the potential divider and then we can change the voltage. That is one way. What is the drawback? Like if you want to change, then there is a losses actually, I square R. Like we have to use the resistance, means there is a losses, I square R. But that's actually is not efficient method. So then people has come with other technology called transistor used in active region. I think in our labs now you could see that the 30 volts power supply, regulated power supply. Have you seen 30 volts regulated? SMPS have you seen? Which one is bulky? Regulated power supply is more bulky because we use bigger heat sink to dissipate the heat because the transistor was operated in active region. The transistor was operated in active region. Can I use board here? Something is there. With hand on, eh? Okay, pencil is there. Fine. Okay, here what will happen was, just imagine that this is the input voltage and this is the output voltage. So in previous days, what they do was the transistor was operated in active region. When they operate in active region, Vg is proportional to Ic. Vg is a function of otherwise Ic. I can write like Vg is a function of Ic. Vg is a function of Ic. So what will happen was, just imagine that if I want to send some current, like this is the like 3 amperes, then the power loss is actually this, though it is like a transistor, but the polarity is like this, plus minus. So plus minus, if 3 amperes is coming like this, then the power loss is given by 3 into Vg. 3 into Vg. So because the transistor we are using in active region, there is a power loss. Okay. So power loss is given by 3 into Vg. For example, instead of the same transistor, if you want to operate, instead of operating in active region, if you operate in cutoff region and saturation region, operated in cutoff and saturation region, what will happen? That means cutoff means saturation. Cutoff means open circuit. Saturation means closed circuit. This is open circuit. This is a closed circuit. So instead of operating the transistor in active region, if you operate the transistor in saturation and cutoff region, then what we can do is we can actually vary the output voltage. For example, like this. So for example, 50% time I was on and 50 time off. Like that, if you do it, then you can actually vary the output voltage. So because the DC voltage is like average voltage, 1 by t 0 to t integral 0 to d f of t dt. If you do it, then with respect to on time, I can change the voltage. But what is the drawback here? Actually, I need a voltage, reduced voltage, but not like like 0 10 0. I need like this voltage. This is my required voltage. But the voltage is like high or low. It is I don't require here. So for this waveform, so we have a ripple factor here. We have ripples actually. This is called as ripples. Now we need to reduce the ripples. How do we reduce the ripples? For example, if we have this kind of waveform, if I want to reduce the ripples, then we use LC filter. Because we want only DC component. We don't want AC component. Okay. So if we simply switch on and switch off, like we will get this kind of waveform, but our desired value is like this. So if you want to get the desired value, then what we do was we should connect a low pass filter. So low pass filter means L and C. But we know that inductor doesn't allow sudden change in current. You should not leave the inductor like that. You should not conduct a current source. Actually, inductor acts like a current source and then switch in series. Okay, that violates the fundamental laws. Therefore, you should allow the inductor to freewheel. So we will connect a diode like this. So this becomes a simple buck converter. How it is a buck converter? The idea is we need to step down the voltage. For that, you connect a simple series switch. If you turn on and turn off, we can regulate the output voltage. But the problem is this has some ripples which is not desired in many applications. Then to reduce the ripples, we need to use a simple LC filter. So we are using LC filter. Then the inductor, we should not leave the inductor like that. We should allow the inductor to freewheel. So for that, we have connected a diode. This becomes a simple buck converter. How do we clear the complete thing? Okay, now coming to a simple boost converter. Actually, boost converter is basically a buck converter. It's a current buck converter. So we know that the transformer is given by transformer relation. V1 I1 is equal to V2 I2. In a transformer, if it is a lossless, we know that V1 I1 is equal to V2 I2. Similarly, a converter, because we are talking about this, switches are operated in on state or off state. In on state, what is the voltage across the device? In the on state, it is 0. When it is off state, what is the current? It is 0. So power is given by V into I. In on state, the power is 0. In off state, it is power 0, ideally speaking. So our assumption is valid that V1 I1 is equal to V2 I2. So for example, if I take V1 is 10 and I1 is 10 and then V2 is 10 and I2 is 10. Then I want to increase the voltage. So I want to increase the voltage to 100. That means 10 into 10. It is equal to 100 into 1. So here I am increasing the voltage, then the current is decreasing. Otherwise, if I decrease the current, the voltage is increasing. Correct now? If I decrease the current, then voltage is increasing. So for that reason, what we do was, you convert a voltage source to current source. What is the how do you convert a voltage source to current source? Practically there is no current sources, but how do you convert a voltage source to current source? No, that is physically, how do you convert a voltage source to current source? Connecting a large value of inductance. Okay, so if I have a voltage source like this, if you connect a large value of inductance, then this will convert like a current source. Now this is like a current source. Okay, this is like a current source. So I can replace like this. Both are same. Correct, na? Now I have like this. I made a circuit like this. This is my circuit. So current source is there. This is some switch here, and this is some load, and this is I0. Okay. Now what will happen? I will draw with respect to I0. I0 I want to draw. I0 is equal to I. When I0 is equal to I source? When S is open. When S is open, I0 is equal to I. Okay. So here it is when S is closed, I will write T on. When S is closed, what is current? When S is closed, the current is 0 because we know that the current flows through the lowest part of the resistance. So when S is closed, I0 is equal to IS. So when S is closed, I0 is 0 and IS is flowing through switch. So like this. In the off state, this is in the off state. In the off state, what will happen? If it is off, I0 is equal to IS. We know that. So what ultimately we are doing, based on if we have more off state, if we have more off state, for example, just imagine that we completely off over a period, it was completely off. What will happen? IS is equal to I0. If it is completely on, what is I0? I0 is equal to 0. Okay, that means we are basically bucking the current. How we are bucking the current? By connecting a parallel switch. Is it clear? We are bucking the current by connecting a parallel switch. So now if you see the circuit, till this is a current source, a switch. Okay, then what should follow? Inductor is there. Then for smoothening the waveform, because we want to get a smoothened, so LC filter is required. L is already there. Then we should connect a capacitor here. Then resistance. Here also capacitor and switch should not connect in parallel because capacitor is a voltage stiff element. See, inductor is a current stiff element, so switch and inductor should not be connected in parallel. Capacitor is a voltage stiff element, like capacitor and switch should not be connected in parallel. Okay, that means just imagine that it is having some voltage. If this is closed, you are making actual voltage abruptly to 0, which is not advisable. So which device will stop discharging the capacitor this side and allow the power transfer this side? A simple diode. Okay, so this is a diode. Okay, this is a simple boost converter. So in a boost converter, it is like a buck converter. It's a bucking the current. Okay, for bucking the current, we connect a parallel switch to the current source. To make the current source, we connect a inductor in series with a voltage source. Then this is how the buck converter is formulated. Hmm? Can someone help? Presentation. Screen sharing here. 1 minute. PC. I think this one, I think. నేను క్లాస్ చేయలేదు అక్కడి నుంచి కదా స్క్రీన్ షేర్ అయ్యేది నేను I think source only. We should go for source. Home. A minute. We got it. Okay, this is how we got this buck and boost converters. Okay, some steady state equations which I don't want to focus much. But one thing is, one important point here is the gain we can derive using voltage balance of inductor and current balance of capacitor also. Generally we talk only this part, but we also can do ampere second balance across the capacitor. We'll get the gain also. Usually if you see any textbook, then they'll give this one. The voltage across inductor you make equal to 0, then we'll get the gain equation. So you can also do the capacitor balance equation, like ampere second balance also. If you make equal 0, then you'll get the same gain. M is equal to IN by naught. Okay. Right? This is some steady state waveforms. Okay, so previously also some design is like, we can talk about design. So this is a design parameters. So for a continuous conduction mode. Okay, this I'm just skipping, okay, because I want to cover more in my other part. Like reliability, you know that in the previous days, in the previous era, people talk about the efficiency, mostly efficiency. Efficiency is one of the important parameter. And then nowadays the reliability also becoming, like, it becomes very vital actually, reliability. So you know that like if you want to purchase something, like we'll see the reliability, whether it is basically reliable or not. Reliable has multiple meanings. For example, if you talk about power system, uninterruptible power supply is one kind of reliability. Similarly, if I talk about phone, like we need to have a continuous signal, so that is one reliability. Okay, so based on the application, reliability terminology will change. But when it comes to here, reliability means a power electronics reliability, where how do you minimize the failure rate? If you are able to minimize the failure rate, then we say that we are improving the reliability. Okay, minimizing the failure rate of a semiconductor device, minimizing the failure rate of semiconductor device or creating the redundant unit. They are two put together is called redundancy. For example, you have inverter, so you see that you design the inverter so that you improve the reliability of the inverter. Otherwise, one more aspect is you just try to create, for the given inverter, try to create a fault tolerance. So even one switch is fault, then you see that other switch is working. That is also where we can regard as improving the reliability, right? So there are some terminology here we need to understand. One is failure rate, mean time to failure, mean time to repair, availability. See, sometimes a simple device will leads to potential economic loss. For example, if I talk about a simple offshore wind stations, if one inverter is failed, then we are unable to generate the wind power. So it is, though the cost of one semiconductor devices may be 1200 rupees, but we are unable to transfer the power. We are unable to transfer the power because of that. So we are losing a lot of power actually. So that word is called levelizer cost. Technically speaking, there was one more terminology called levelizer cost. So levelizer cost means it's not about the cost of a simple product. It is about the cost of a complete system, including the charges of energy. So as I told, like if you talk about a wind station, wind can produce some power, like it can produce 1 megawatt power. If there is a fault in the inverter, we are unable to feed to the grid, then that 1 megawatt is wasted actually. 1 megawatt into 100 hours. So it's a waste of energy. We are unable to use it. So it is always important to improve the reliability. So availability is also a parameter in the reliability, because for example, if I want to replace the same semiconductor devices, then we need to see the availability of the semiconductor device. Then how much time it takes to replace that. So it also plays an important role now. Okay. So sometimes reliability in case of, especially in case of naval applications or defense applications, it should be very high. It should be much more reliable than any other application, because we are aiming human resources actually. If the system is not reliable, then it leads to a human life damage. Then some ways of reliability estimations, and these are different techniques actually. One is military handbook. Mostly people are working in this area, like military handbook. Through military handbook 217, like people talk about reliability, and then like fights, and then physics of failure rates. These are some estimations, okay. And then some research areas like how do you manage the electrical stresses. So why I am talking all this area is a new way of seeing the converter improvement. For example, previously people talk about only efficiency, but how do you see the converter performance? It's not only efficiency, but there are some other parameters also. So from the reliability perspective, some of the research areas going is, one is management of thermal and electrical stresses. For example, like that the power semiconductor devices are more tend to fault when they subjected to temperature like an increase in temperature beyond its rated value, because they are more temperature fragile, and then if temperature go beyond some value, it fails actually. So what we generally do was, in order to meet the temperature of semiconductor device within the limits, then we use a heat sink. Then designing a heat sink is one important aspect. Then selection, of course, selection and designing. Sometimes we always need not design everything. We can simply identify like whichever is feasible, and then selection is one parameter actually. So from industry perspective, selection is one important parameter. Similarly, thermal stresses means voltage stress and current stress. Electrical stresses means voltage stress and current stress. Thermal means temperature. Temperature is basically with respect to losses, power losses, majorly power losses, both conduction losses and switching losses. In case of in case of switch, there are two losses. One is conduction losses and another is switching losses. Both the losses will constitute to increase in temperature. Unless you release the temperature to the environment, then semiconductor devices fail. So the one important area is, how do you manage the thermal and electrical stresses? Electrical stresses means zero voltage switching and zero current switching is one important area, like people are working. And then circuit topologies. Like as I told, like in order to go for reduce the electrical stresses, like multi-level inverter is one inverter where we reduce the voltage stress of the switches. Multi-level inverter, one of the advantage of multi-level inverter is we reduce the voltage stress of all the switches. That means reducing the voltage stress actually is one way of improving the reliability. Okay. And then people also talk about control strategy. For example, I use two switches together. Then if I see that one switch is getting heated, then I operate the second switch, parallel switch. Is it clear? That is how we can actually do some control strategy in limiting the thermal strategies. People are looking about it. Then real-time simulations. That means previously, like like everything we used to test physically, but people are developing some real-time simulations to check the reliability. For example, we know that general MATLAB we used to do we find the inverter efficiency as well as we can find the voltage across switch, we can find the current through the switch. Then what we can do was the same MATLAB we do in in a real time, rapid real time Opel RT people are doing, and then they are basically making the model of the exact system, and then they are finding the reliability also. Okay, so on reliability there are so many simulation tools has come. It's not about only efficiency. On reliability itself, like using some Monte Carlo techniques, they used to give the mean time to failure, and then ultimately what they do is they do design for reliability. So ultimately this real-time simulations will help us to do design for reliability. For example, like I say the inverter I am purchasing from the market. So the market may give 1 year warranty, but while designing, like what we can do is I want to design this inverter for 10 years. That is my target. That means we are actually taking care of lot of environmental parameters, and we should see that this inverter has to withstand all the external environment parameters, and then it should work a minimum of 10 years. That is called design for reliability. So wherein we consider all the parameters like the load profiles, okay, as well as the source profiles, and then how the voltage test is coming on the switch. Okay. Okay, some like one review paper if you see now, like which device is more, actually this review paper is like an industry survey based survey for reliability in power electronic converters. It was published in IEEE Transaction 2011 itself. Actually these are some companies actually where the review comments is given by. One is aerospace industry, automobile industry, and then motor drive industry, and then component manufacturers. So there are some questions it was in the reliability with respect to reliability. Like one is which device is more fragile component, means which tends to more fault. So if you see that power devices has a large share because they are more tend to fail. That is what the survey says. Yeah, I leave. Yeah. And another is which are the likely causes of failure. What are the likely causes of failure? What are the one is they say environment is nothing but because of like vibrations because of vibrations or transient conditions or heavy load or overload. These are some reasons, the causes of failure. And similarly, failure cost ratio. You see this. Like greater than 80 is here. Greater than 80 is here. What is meant by failure to the ratio is sometimes though the equipment cost is very small, but the small equipment can lead to a potential economic loss, which I told previously. A far away wind plant is there, offshore wind plant is there, though the semiconductor device cost is very small, but if it fails, then the impact on the energy production is very high. So sometimes if you see though the switch cost is very small, but the potential revenue loss is very high. So that is the measure of this failure to the cost. And then how do you improve the reliability? Like how do you improve the reliability? So one is using the larger heat sink. Then if the capacitors are there, if you want to reduce the failure of the capacitor, connecting the parallel capacitance. Okay, these are some methods actually. Increasing the coolant, voltage suppressors. Like we know that we use snubber circuits like for creating a dV by dt production and dA by dt production. Okay, so not that much important, but only one slide, one point I want you to understand was, so in this, like here we always talk reliability in terms of failure rates. In the literature, the reliability we generally talk in terms of failure rate. The failure rate, if you see the MOSFET or diode or inductor, it mainly depends upon pi t, where pi t is a temperature factor. Pi t is a temperature factor. Here you see. Failure rate of a switch, failure rate of a diode, failure rate of inductor, failure rate of capacitor depends upon pi t factor. Pi t is again is a function of losses. So here you can see that P switch is D. It's a function of actually this T is a function of like losses here. Okay. So take away from this slide is the stress, the electrical stress is converted into temperature. The temperature will be converted into failure rate. Okay. So temperature and failure rate are both are relative. If the more temperature is there, then the failure becomes more. Okay, that is what, so inference from this slide. Okay, and then as we told that, like, in the previous case, like the DC-DC converters which we discussed previously, they are basically called hard switched. Okay, they are called hard switched devices. They have a switching losses. If you have switching losses, then the temperature rise will be very high. When the temperature rise is very high, then it tends to fail. So in order to address that, then people was going for soft switching converters. So we'll have a tea break now, then we'll discuss later. Okay. ఈ స్లైడ్ లేదా అండి, స్లైడ్ లేదా?